So hello everyone. In the last few lectures, we talked about Newton's first law and second law, okay? And we also understood the concept of different kind of forces like gravitational force. Then we talked about the frictional force, and then we talked about the tension force, right? And in the last class, we also calculated that when a body is attached with a pulley, then we can find the acceleration of that object, right? Now, let us move further and let us talk about the third most important law, that is Newton's third law, okay? So, what does this law says? That when two objects are in contact or not, okay, they exert equal and opposite force on each other. Okay, you might have heard that we say that for every action there is equal and opposite reaction. What is the meaning of this statement? That if two bodies are there, whether they are in contact or not, they exert equal and opposite force on each other. Okay, so another statement is, for every action there is an equal and opposite reaction. Let us now understand what is the meaning of this statement. For example, you might have also learned Newton's law of gravitation, right? What? That if two objects are there of mass m1 and m2, then the force between them is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. That is also a result of Newton's third law, right? So basically, it's a two objects are there. In that case, the two objects are not in contact, right? But they exert equal and opposite force on each other, right? Another example of Newton's third law: if two charges are there of charges q1 and q2, they exert equal and opposite force on each other, and the electrostatic force again is directly proportional to the product of the charges of the two bodies and inversely proportional to the square of the distance between them. Okay, this is how much is the force, but Newton's third law statement is that they will exert equal and opposite force on each other, right? Another example in our day-to-day scenario, for example, a boy is there and the boy kick a ball, okay? Now, the boy has exerted force, for example, F on the ball, then the ball will exert equal and opposite force on the boy, okay? But to our surprise, not surprise, we observe that the ball is flying in the air, but the boy does not, right? Why? We'll understand that. But the first most important thing to understand in Newton's third law is that the two forces which I am saying, they are equal and opposite, they are on the different bodies, okay? Why this is important? Because sometimes the students, they get confused with the Newton's first law, right? On Newton's first law, when I talk about the net force, then that is the net force on one body, okay? Here when I am saying that the two forces are equal and opposite, they both are on different bodies, okay? So another important statement which one should remember is that both the forces act on different bodies, okay? When I talk about the net force, it is on one body, okay, for the Newton's first law and second law, okay? When I say that the object will be at rest or in uniform motion until and unless an net unbalanced force acts on it. Then I am talking about one object, net force on that object. If the net force on that object is 0, the object will be at rest. Okay, there won't be any acceleration. So from Newton's second law, F net is equal to mass into acceleration. F net is 0. It means all the forces will balance each other. When I am talking about Newton's third law, then I am talking about two objects. For example, an apple and earth. Right? Apple, if I leave an apple, apple is attracted towards the earth. Right? Why? Because of the gravitational force. But you should remember that apple is also exerting equal and opposite force on the earth. But we do not see earth rising. We see apple falling. Right? Why? The forces are equal. The reason for that is the mass of the object. Okay? Let us see that. Okay, I hope this statement is clear. In contact or not, they exert equal and opposite force on each other. Now, for example, a boy kicks a ball, okay, of mass m, and boy's mass is boy of mass capital M, right? Then, so this is a boy and this is a ball, its mass is capital M and the mass of the ball is small m, right? It exerts force F on the ball, then ball will also exert equal and opposite force on the boy's foot, okay? Okay, this point should be clear, and these two forces are acting on different bodies, on the boy and the ball, right? But now, in order to understand, because many students, they have a wrong intuition that because the ball is flying in the air, the force is more. No, right? The man is exerting force on the ball, F, and the ball is also exerting equal force on the man's foot, right? So force on the boy is equal to force on the ball, right? Now from Newton's, so this is, what is this force? Net force on the boy. From Newton's second law, this net force on the boy will be mass of the boy and the acceleration of the boy, right? This will be equal to mass of the ball into acceleration of the ball, okay? And from here, you can observe that mass of the boy divided by mass of the ball, that will be equal to acceleration of the ball divided by acceleration of the boy, right? Now, the acceleration is inversely proportional to the mass. So, and the mass of the ball is very, very small. That is why the acceleration of the ball is huge, whereas the mass of the boy is more, right? So, its acceleration is very, very small. That is why you see the ball flying. It's not because the force is more. The forces are equal and opposite from Newton's third law. They have to be, right? Exactly similar example is when the apple falls towards the earth. Then the apple is exerting how much force on the earth? Mass of the apple into mass of the earth divided by the distance square between them, right? That is Newton's law of gravitation. Similarly, earth is also exerting force on the apple, how much? Mass of the apple into mass of the earth divided by the distance square, right? But the mass of the apple is very, very small, so its acceleration is huge, right? So you see apple falling, whereas the mass of the earth is very, very large, the acceleration is very small, negligibly small. You don't see earth rising, okay? This is the meaning of Newton's third law. So there are many various examples where you can argue that why one object is moving, why other is not, but the forces are equal and opposite. Another very classic example of Newton's third law is, which is asked in most of the books, that if there is a horse attached with a cart, okay, and if horse and cart, they both are exerting equal and opposite force on each other, then how the cart is moving? Pause the video and think. So from Newton's third law, if there is a horse, right? Okay, just I am drawing a rough diagram, and there is a cart, right? They exert equal and opposite force on each other, horse and the cart. They both exert equal and opposite force. Then how it's moving? So that is correct. There is no problem in this statement that they are exerting equal and opposite force. But whether the object will move or not, that will depend upon the net force on that object. So that is fine. They both are exerting equal and opposite force on each other. But whether the horse will move or not, that will depend upon the net force on the horse. That is not zero. Okay? These two forces are on two different objects, and whether the horse will move or cart will move, that will depend upon the net force on the horse and the net force on the cart. Okay? So here net force on the horse is not zero because there are other forces. Horse is applying force on the ground and the ground is applying force on the horse. So the net force on the horse is not zero, that is why it's moving. Similar argument is for the cart. Okay? So one has to be careful whether I am talking about the net force on an object or I am talking about the two forces which are equal and opposite on two different objects. Okay? Now let us do some problems of connected bodies where we have to calculate how much amount of force that object is exerting on the other object. Okay? Let us do that. Okay. Let us start with a very simple problem. Okay. So I will be solving the problems in the form of symbols. Okay. Then you can practice by putting numbers and you can calculate. Okay. But a very important tip is in physics for solving problems is that you should always first find the result in terms of the symbols, and then at the end you should put the numbers and get the numerical value. Okay. How this helps? Because when you put symbols, at the end whatever result you get, you can see whether that result is correct or not by checking the dimensions. Okay. For example, on left hand side, if we have a dimension of acceleration, then on right hand side also whatever is there, you should get the dimensions of acceleration. That is a very nice check for solving problems in physics. Okay. Let us do that. The first problem, a very simple one. For example, if there is a table, I am not including any friction. There are two objects of masses m1, m2, and they both are being pushed by F. Okay? Two objects are kept on a frictionless table. Okay? Or in all these problems, you can just add friction and calculate again. Right? So at present, I am just taking the simpler case. Then we will add friction and solve. Are kept on a frictionless table. Right? So what you have to calculate? Table and pushed by force F. Calculate the acceleration of two objects, of both the objects, both the blocks, and B, calculate the force exerted by m1 on m2 and vice versa. Okay, this is the first problem which you will encounter in case of connected bodies. Okay, now the first assumption is that both the bodies are moving together, so both will have same acceleration. Okay, and the net force is in this direction, so I am taking this direction of acceleration and this direction to be positive. Okay, now whenever we have connected bodies, then in order to find the acceleration, that we can find directly, but in order to find the force between these two bodies, because from Newton's third law, m1 will exert some force on m2 and m2 will exert equal and opposite force on m1, right? In order to calculate that force, we need to draw what is called as free body diagram, okay, that I will show you. But first, let us understand how to calculate the acceleration directly. So these two bodies are moving together, right? So in order to find the acceleration, the force which are being exerted by the two blocks on each other, they are the internal forces. They will not play any role in order to calculate the acceleration. The net force on this object is F, right? And the total mass is m1 plus m2, right? Because these two objects are moving together, so you can assume that these total to be one block of mass m1 m2. So now it becomes very simple. So this will be equivalent to, considering one block of mass m1 plus m2 and force F is being exerted on this. So you can find directly the acceleration from Newton's second law, F net divided by m total. That will be equal to F over m1 plus m2. Okay, this is a simpler way to find the acceleration directly, but we can also find the acceleration by using free body diagram. Okay, but I hope this is clear, because I am assuming that both the objects are moving together and they are having same acceleration. Then you can directly use that. You can assume this to be one block. Okay. Now let us understand what is the meaning of free body diagram. Whenever there are two objects, okay, and they both are moving with A we have already calculated, but I will show you that we can calculate again. The free body diagram is m1 will exert force on m2, let me call this as F1, and m2 will exert equal and opposite force F1 on m1. Free body diagram means that you separate these two blocks and draw all the forces acting on m1 and m2 separately. Okay. So for example, the forces on m1 are F and the force F1. Okay, and they both are, and it is moving towards right. What are the forces on m2? F1. You will not take F on m2. You will only take the forces which are applied directly. Okay, for free body diagram. This is called as free body diagram. What is the meaning of this? That you draw all the forces acting on that object directly, and then we apply Newton's second law, right? Now apply Newton's second law of motion. So from on m1 it is moving towards right. F net is equal to m1 into A, right? If somebody asks you how much is the net force on m1, mass into acceleration. Acceleration we have already calculated. You can directly substitute the value and find. Okay, but let me calculate again for you. How much is F net? F is in right direction, F1 is in left direction. Force is a vector quantity, so you have to take the vector sum of the forces. So F plus F1 that is a vector sum, but F1 is in opposite direction, so it is negative, right? If I am considering right to positive direction, left will be the negative direction, okay? That we have already learnt in vectors. If you have forgotten, again go back and review my 2 lectures on vectors. So Fnet is, and I am taking, the object is moving towards right, so the direction of net force is towards right. So Fnet will be F minus F1 is equal to m1 into A. This is equation number 1. Okay. One way is to, we have already calculated the value of acceleration. We can substitute the value of acceleration and calculate F1, right? But I am not doing that. I want to calculate again the value of acceleration, okay, by using free body diagram. Now, applying free body diagram, applying Newton's second law on M2. So, how much is the net force on M2? F1, okay, that is towards right. So, F1 is equal to M2 into A. Now, these are two simultaneous equations and there are two unknowns, F1 and A. Number of equations should be equal to number of unknowns. Then only you will be able to calculate. That we have already learned when we solve simultaneous equation in maths, right? So, if number of equations are equal to number of unknowns, you can calculate the unknowns, because F is known here, right? And masses are also known. So, substituting the value of F1 from equation 2 in equation 1, we get F minus M2A is equal to M1A, right? F is equal to M1A plus M2A, and from here we can calculate that F over M1 plus M2 is equal to A, and this is the same result which we got earlier when we calculated directly the value of acceleration. This is equation 3. Now, this is the acceleration with which the two blocks will move. Now, how to find the amount of force exerted by M1 on M2 and M2 on M1? We can just substitute the value of A into equation 2, right? So, that will give you F1 is equal to M2, A is F over M1 plus M2. This is the value of the force exerted by, okay. So, let me write it here also. This is the acceleration with which the two objects will move. This is the amount of net force, right? And this is the amount of force exerted by the two objects on each other, right? And also, I have just assumed the direction of the force. Here, if you calculate from this, you should get the same value. You can also use the equation number 1 to calculate F1, okay? So, this is the amount of force exerted by M1 on M2 or vice versa. Okay, I hope this is clear, right? So, this is the most basic example of the connected body, where we can calculate the amount of force exerted by one body on another, okay? Similarly, we can also calculate, for example, if there are 3 objects stacked on one another. The only difference will be there, that in that case you have to take care about the gravitational force, okay? How do we calculate that? We can just, the concept remains the same. We can just keep on adding little bit complications, okay? We will do more problems in the future videos, okay, of connected bodies, okay? See you then.